Alright guys, so this should be the second hand calculation video that you guys should be watching. The first one should have been over the methods, the hand calculations for coming up with the equations for the internal shear and moment of the beam. You guys probably shouldn't have had to watch a video over that if you needed to. We've been doing that for a while this semester. But now we need to look at figuring out our equations for calculating our stresses, right? So we need to calculate the shear stress and the bending stress, the maximum shear stress and the maximum bending stress on this beam cross section, right? So those shear stress is VQ over IT and bending stress is MC over I, right? So we've already got the shear and the moment from the other equations, and everything else is pretty easy to calculate. But we also need to, but first we need to calculate the moment of inertia in terms of our parameters that we've been given for this beam cross section, right? So we've been given B sub F, T sub F, T sub W, and D, right? B sub F is the width of the flange, T sub F is the thickness of the flange, T sub W is the thickness of the web, and then D is just the overall depth of the beam itself, all right? This is typically how I-beams are classified here. This is the dimensions that we're given for I-beams normally. So let's go ahead and jump in. We need to calculate the moment of inertia of this I-beam so we can calculate both the shear and the bending stress, right? So let's start off with moment of inertia, right? So moment of inertia, I, in terms of our parameters that we've been given here, we can, since this is a symmetric, we're just going to assume all of these I-beams are symmetric. Most of them are, right? So I want to come up with the equation of the moment of inertia in terms of these four variables, so that we can plug it into our formulas. So what we're going to do is we're going to take the BH cubed over 12 for the entire overall dimension of the cross section, the total out to out, and then we'll subtract out the negative space. We've done this trick several times in class now. So if we do it here, what we're going to get is B sub F is the B D cubed over 12, right? So that's BH cubed over 12 for the total out to out area of the cross section. Now we're going to take out the negative space. So we're going to say minus the width of the negative space is B sub F minus T sub W. And then the height of the negative space is D minus 2 times the thickness of the flange cubed over 12, all right? So that covers our moment of inertia, right? So that's our equation for moment of inertia. We'll plug that equation into the Excel spreadsheet here in a minute, all right? The next little section property that we need to calculate is our Q, right? And so we'll do that here. We'll say that Q is equal to A prime times Y bar prime. And we're just going to add up A prime and Y bar prime for each of the shapes, right? So we'll start with the top flange. We're trying to calculate the maximum shear stress at any location X along the beam. So maximum shear stress occurs at the centroid. So our A prime is all the area above our neutral axis, right? So we'll start off with the first A prime being the top flange, that area of that top flange being B sub F times T sub F. So B F TF, that's the area, and then the distance, the Y bar prime for that top shape is going to be the distance from the centroid of the top flange to the neutral axis of the overall shape. So that's going to be D over 2 minus T sub F over 2. Okay, so that's A prime and Y bar prime for the first shape, which is the rectangle here. Okay, now the second shape is going to be this shape, where the area of that is equal to, we'll say plus here, the area of this is equal to T sub W times the height of this, which is d over 2 minus t sub f. Okay, so TW times d over 2 minus t sub f, that's the A prime. And then the y bar prime is going to be equal to half of the height of that shape, which is half of d over 2 minus t sub f. Okay, so that's it. That's Q for the for all of the area above our neutral axis. Okay, so we're going to take these two equations and take them into our Excel spreadsheet. For beams 2 and 3, you will need to do these same procedures, except you'll need to figure out what I and Q are for the pipe and for the channel. So we're working through the beam number 1 together. So this is what you need to know for beam number 1.